we have our next speaker with us, Dr. Nazar Hussain. He is the alumni of University of Jammu. He has done his master's in organic chemistry from University of Jammu. And after that, he completed his PhD in chemical sciences from CSIR lab of Jammu, Indian Institute of Integrative Medicine, that we call IIM. Then after that, he completed his postdoctoral research at INRS, Canada. His area of interest in chemistry includes development of novel methodologies for carbon-carbon bond formation carbohydrates, total synthesis of biologically potent molecules and marketed drugs, medicinal chemistry, carbon-hydrogen activation, and functionalization. He has many publications of national and international repute to his credit and many book chapters to his credit. Nazar sir, can you hear me?
Thank you, ma'am, for your kind introduction.
Yes. So welcome to the session. Kindly share your presentation with the students. Over to you, sir.
Okay, thank you, ma'am, for your kind introduction. A very good morning to all. I would like to thank Principal Sir for the invitation and the whole organizing team of this conference, the chemistry department, and especially my friend Dr. Fahim for invitation and sending me update time to time. So we have a nice lecture from Dr. Anju ma'am on enzymatic reactions. So keeping the thing continuity, the organic reaction. So I would like to share some of my work on CH activation in carbohydrate, and I'm going to show some of our recent results in this area. Basically, CH activation is the cleavage of unreactive CH bond followed by CC. Just 1 minute. CH activation is the cleavage of unreactive CH bonds followed by CC-CX bond formation with the elimination of H2, and that gives rise to the formation of some functionalized molecule. The importance of CH activation reaction is that it is a one-step process. So it's really an atom economic, step economic. So in order to activate a particular center, CH activation reaction works. So functionalization at a particular centers can be happen by utilizing this strategy. So in this, another important feature of these reactions are this strategy is really, in this strategy, there is no need to pre-functionalize the substrate. So late stage functionalization of some of the biologically active molecules are also takes place by utilizing these reactions. So if we compare the traditional cross-coupling reactions with CH activation reaction, traditionally the cross-coupling reactions require an extra step to pre-functionalize the substrate before coupling with other partner. So we know that some of the named reactions like Heck reaction, Suzuki reactions, Steele and Higashi and other reactions, they use some of the substrate they are previously activated. Like in traditional cross-coupling reactions, the X could be chlorine, bromine, iodine, or triflate. This moiety couple with other coupling partner, and this other partner is also pre-activated. The Y can be tin, boron, zinc, and magnesium. And they result the formation of this CC bond form. So this is the named reaction like Suzuki reaction. In Suzuki reaction, actually any organic halide coupled with boronic acid. But in CH activation reactions, this strategy doesn't require any pre-activation. So simple CH bond can be utilized for the activation to form this linkage. This linkage might be CC, CN, or CO. CH activation reactions can be directed or non-directed. In non-directed CH bond activations, like in arenes, where all the CH bonds are equivalent, or we can say that are equally reactive. So only one CH bond can react with the other coupling partner to form this CC linkage. But in some substrates, like in toluene, where this methyl group have some influence on this ring. And in this case, the CH bond at ortho, para, and meta have a different reactivity. So in this case, there is a possibility of formation of different regioisomers. In order to solve this problem, directing group plays an important role. Like any arene have a directing group, like in this example, this directing group influence this CH bond at ortho position and selectively activate this position, not the other CH bonds. So a selective formation of these molecules can be takes place by utilizing directing group in CH activation. Basically, we are working on carbohydrate chemistry and we are using sugars. We are synthesizing some of the biologically active molecules by utilizing sugars, mostly monosaccharides. And recently, we have synthesized some of the biologically active molecules, like in total synthesis of alpha amino KDO sugars. We have completed the total synthesis of dapagliflozin. This is an SGLT2 inhibitors, and these molecules have been utilized in the treatment of type 2 diabetes. We are also interested in the synthesis of some of the bacterial molecules, like recently we have completed the total synthesis of these two molecules, gladuside 1 and gladuside 2. At the same time, we are also interested to utilize sugar in CH bond activation reactions. We have completed some projects in this approach also. At the same time, we are using sugar in the synthesis of some chiral aromatic building blocks. And we are also interested in cross-coupling reactions of sugars. In carbohydrate, basically we are working on glycal. Glycal, it's a derivative of any monosaccharides, like we are using different sugars like glucose, galactose, rhamnose, and other. And by using these commercially available sugars, we can easily synthesize this moiety that is glycal. So glycal can be from glucose, can be from galactose, or rhamnose and xylose. The important feature of this molecule is that such type of molecule contain the double bond at C1 and C2 position. And the reactivity of these two carbon is quite different because of the presence of this ring oxygen. So C1 position is highly electrophilic due to ring oxygen. At the same time, the lone pair of oxygen is in conjugation with this double bond that makes the C2 position nucleophilic. So such type of reactivity in glycals can be utilized for the synthesis of different substituted sugars. Like one of the most important rearrangement is Ferrier rearrangement. Under Lewis acid, glycals form this oxocarbonium, and any external nucleophile results the formation of some glycosides. At the same time, under some strong basic condition, the C1 position can be metallated and can be utilized for some cross-coupling reactions. So if we have a functional group at C2 position, like X can be nitro or formyl group. So electron withdrawing effect of this group imparts a different reactivity at C1 and C3 position. So a selective formation of different burned sugars at C1 and C3 could be possible. So at the same time, if we have a halo group at C2 position of this glycal, such type of derivative could be utilized for the synthesis of C2 branch sugars and some enolated sugars. So glycal is really an important derivative of carbohydrates. These molecules have been successfully utilized in the synthesis of some of the biologically active molecules in the total synthesis of various drugs like dapagliflozin. Starting material is glycal, and this virginium, this molecule is isolated from Virginia ciliata, and the total synthesis of this molecule have been successfully completed by utilizing glycals and some other biologically active molecules like aspergillite, vitrixin. All these molecules could be possible, could be synthesized by utilizing glycal as a starting material. So next is the palladium catalyzed CH activation and functionalization in glycal access to chiral aromatic building blocks. So initially we thought that in case of glycal, there are two CH bonds, that is two sp2 hybridized carbon. And in presence of some metals like palladium, these glycals might form this pi complex with the palladium, and then insertion may take place at C2 or C1 position. And if the insertion of palladium takes place at C1, it's not stable due to ring oxygen, and we thought that a selective C2 activation could be takes place, and this results the formation of this dye. So the major challenges in this approach is the selective activation of CH bond, either C1 or C2. And also we are working in carbohydrate chemistry, and carbohydrates have a different protecting group, different free OH in the sugars. So we need a mild reaction condition so that all the protecting groups could be survive under that particular reaction condition. And at the same time, we need to derivatize the sugars. So compatibility of various sugar derivative is also an important aspect in this strategy. So we search in the literature and we find that there are two ways to get these C2 branch sugars. One is by utilizing two formyl glycals, and by Wittig olefination, this results the formation of this diene. Another approach is by utilizing two haloglycals, and under Hack reaction, this CC bond formation is already reported in the literature. So the importance of such type of sugar is that these molecules have been utilized in the synthesis of this bradyrhizose. These molecules is supposed to help in the nitrogen fixation of plants. So we thought that without pre-functionalization of this glycal, we activate the C2 position of glycals. And after rigorous optimization of various conditions, we finally come to the conclusion that by utilizing palladium acetate 10 mole %, silver acetate 2 equivalent, and in a mixture of DMF and DMS, so 20:1, this is really important for the reaction. And at 80 degrees Celsius, by utilizing any terminal alkene or a cyclic alkene, this leads the formation of C2 branch diene and this allylated sugar by utilizing this cyclic alkene. Because in case of cyclic alkene, there is this hydrogen atom. So I will explain in the mechanism why this is allylated and alkylated. Next, we went for substrate scope, and we prepare a library of compounds by utilizing different cyclic alkenes and different sugars. Like we utilize cyclohexene, cycloheptene, cyclopentene, and cyclooctane, and various other sugars like benzylated sugars, like OPMB protected sugars and OBZ protected sugar. In all cases, we got a reasonable yield. So next, we utilize some terminal alkenes. In terminal alkenes, we utilize some styrenes, substituted styrenes like 4-bromostyrene, 4-acetoxystyrene, and some activated alkenes like methyl acrylate, and some other sugars like ether protected sugars, benzylated glucals, some other sugars like ramenol. In all cases, we got a very good yield. Next, we utilize a furanose form of the glycals, and in this case, we prepare some compounds of 3C substituted sugars by utilizing same optimized reaction condition. So, so far we have synthesized a library of organic compounds, this diene. Next, we thought that can we utilize this diene for some aromatic compounds. So we utilize this arene precursor in the presence of base. This form this benzene, and we thought that the 4+2 cycloaddition could lead the formation of this compound, but later on under basic condition, this ring aromatized and the sugar moiety opens up. So this leads the formation of this naphthalene, the chiral naphthalene. So it's important to mention here that this is only one report in the literature so far that for the synthesis of chiral aromatic building blocks. So this is a one-step process for the synthesis of aromatic chiral aromatic cores. 4+2 cycloaddition followed by 1,1,5 hydrogen shift leads the formation of this compound, and we utilize arenes as a source of dienophile. Again, we prepare a library of compounds by utilizing different types of dienes, and we synthesize different substituted naphthalenes. We varied some arene precursor also. We utilize 4-methoxyarenes, 4-methyl dimethoxyarene precursor. We at the same time we utilize some different sugars like ramenose, glycal derived from ramenose, and glycal derived from xylose, and some other protected sugars like ester protected sugar, OBZ protected sugar, acetate protected sugars, and we synthesized a library of compounds of these chiral aromatic compounds. Next, we thought that can we synthesize some phenanthrene molecules from naphthalene by utilizing same strategy. For this, we utilize the naphthalene-based arine precursor. So in this case, under same mechanism, we got a mixture of 1:1 ratio of mixture of residue isomer. Because this arine is not symmetrical, so there is a possibility of formation of two structural isomers. And OBZ protected dynes also give the same results. So in this way, we successfully synthesized 1,3-disubstituted phenanthrene derivatives. Next, we thought that can we utilize this C2 aryl glycals for the synthesis of 1,5-disubstituted phenanthrene derivative. So in this case, we first utilize this OBN protected glucol. First, we iodinate at C2 position, then Suzuki coupling leads the formation of C2 aryl glycals, and then the arynes. So in this case, this molecules behaves like a diene, and similarly in this case we synthesized 2,5-di, not 1,5, 2,5-di substituted phenanthrene derivative. In this case, first is the 4+2 cycloaddition reaction, and then the similar 1,5 hydrogen shift. So in this case, 2 ring gain aromaticity at the same time. So this is the driving force for the formation of this phenanthrene derivative. This is a synthetic utility of this approach. We utilize some of our synthesized molecules for the synthesis of some of the substrate for aldolases. So this is the substrate utilized in aldolases, utilized by aldolase enzyme, and we successfully oxidize this hydroxy group by utilizing acetic anhydride and DMSO to give this keto compound. At the same time, deacetylation of this molecule is the formation of this tetrol, and then by utilizing sodium periodate, this leads the formation cleavage of this tetrol, and selectively we form this meta-disubstituted naphthaldehyde. It's really difficult to form such molecules by utilizing simple naphthalene. So next, we thought that can we utilize a similar kind of glycals like a pseudo-glycal for the functionalization at C2 position. And we utilize similar conditions before we utilize for glycals having a double bond at C1 and C2 position. But in this case, reaction didn't work. So this experiment confirms that by utilizing this condition, the ring oxygen has an important role in the CH activation at C2 position. So we thought that can we activate this unactivated CH bond of pseudoglycals? In this case, the double bond is at C2 and C3 position, not at C1 and C2 position. So under this strategy, we thought that can we launch a directing group at C1 position that might play an important role in the activation of this unactivated CH bond. So in this strategy, initially we did a Fourier glycosylation reaction with this N-hydroxythalamide by utilizing some Lewis acid to get this compound, and then the cleavage of this thalamide with hydrazine hydrate in ethanol to get the free amine, and then the acetylation with acetic anhydride and DMAP leads the formation of this protected NHOAC as a directing group. Next, we utilize this directing group under palladium catalysis, and to our surprise that the activation of this C2 position of pseudoglycal takes place successfully. Next, the catalytic cycle, how this directing group plays an important role in the activation. Initially, palladium acetate coordinates with this nitrogen atom to form this 5-membered pallado cycle. This cycle is really important to activate this C2 position of pseudoglycans. And next is the coordination, alkene coordination to form this complex, and then alkene insertion, and finally the beta hydride elimination leads the formation of this diene by utilizing directing group. And the elimination of HPDOSC, then reductive elimination and further oxidation of palladium 0 to palladium acetate by silver oxide. Again, we prepare a library of compounds by utilizing different alkenes like methyl acrylate, butyl acrylate, tertiary butyl acrylate, and then some styrenes, substituted styrenes, And we did a variation in some sugar also. We utilized galactol, we utilized ramnol derived from ramnose sugar, and some variation at the protection of NH with some different protecting group. In all cases, we have seen that the reaction is very compatible, the reaction is very mild, and some of the silyl protected group like TBS protected sugars also works in this reaction condition. So, in summary, we have developed some efficient strategies by utilizing sugars as a starting material for the synthesis of some C2 branch sugars by utilizing CH activation reactions, and at the same time we utilize some of the sugar for the synthesis of chiral aromatic building blocks, and with some pseudoglycans in which the directing group plays an important role for the activation. So by launching a directing group at C1 position, leads the formation of the C2 branch sugar. This manuscript is under revision in DOC. So I would like to thank Principal Sir for and the whole organizing committee for sending me the invitation. I would like to thank Banaras Hindu University for giving me the startup research grant, my supervisor at CSIR Plan Jammu, my postdoc supervisor, Professor Charles Gauthier, and all the funding agency. And I would like to thank all the reviewer for your kind introduction. Thank you very much.